Krzys, and welcome to episode 4 of the Sutton program, hosted by GU Rocketry and sponsored by RS Grassroots. Today, we'll be discussing the origins of rocket propulsion, exploring the fundamentals of how to convert pressure into thrust, and learning a little bit about modern propulsion systems. To really understand how the largest and most complex propulsion systems, like the Saturn V F1 rocket engine or the Space Shuttle solid rocket boosters work, it's important to recognize and appreciate the history of these systems. There's no better place to start than with the father of modern rocketry himself, Dr. Robert Goddard. In his paper, A Method for Reaching Extreme Altitudes, Goddard postulated that it'd be possible to send a rocket into space by burning a high-energy gunpowder in an enclosed chamber and using the hot gases to accelerate them through a special type of nozzle called the converging-diverging nozzle to very high velocities, which would allow the rocket to reach the upper atmosphere and space. Now, at the time, Goddard was mocked for his theories that a rocket could go to and operate in space. After all, most of the general public thought that rocket couldn't even work in space where there is no air. And that's because there was a common misconception that the rocket engine exhaust actually pushes up against the atmosphere, which gives it thrust. Now, we learned in episode 2 that that's not actually true, and that the rocket acceleration is actually governed by Newton's laws and the conservation of momentum, which causes the rocket to accelerate. Here's a closer look. First, let's assume we are in space, and there is no gravity. Then let's say that this is our rocket with a mass of 100 kilograms, and 80 kilograms of that is going to be the propellant inside of the rocket. That makes the remaining 20 kilograms our rocket's structural mass. Now let's go ahead and write out the rocket's momentum here, but we'll keep the masses separate. This is going to be our rocket structural mass plus the rocket propellant mass. Since the rocket is at rest, we know the velocity is 0, so the total momentum is also 0. But we can make this more interesting. Let's now throw 10 kilograms of the propellant overboard from the bottom of the rocket at a very high velocity of around 100 meters per second. The momentum of this propellant then becomes 10 times 100, or 1,000 kilogram meters per second. But Newton's laws tell us that momentum must be conserved. So this means that the rocket must now have a momentum in the equal and opposite direction. And to solve for it, we first set the propellant momentum and the rocket momentum equal to one another. Then subtract that 10 kilograms of propellant that has been released from the rocket earlier. And then using this new mass, we can calculate how much that rocket's velocity has changed. Now, looking at this relationship between the momentum of the exhaust and the momentum of the rocket, we can deduce that there are two ways that we can actually increase the velocity of a rocket. And that's because the mass of the rocket is going to stay constant, at least at an instantaneous point. So that means that we can either increase the amount of mass that we are throwing overboard, or we can increase the velocity at which we throw that mass overboard. And it's these two very simple principles that govern propulsion systems. And fundamentally, that's what Goddard described in his paper. And he showed that it actually is possible for a rocket to operate in space. And the rest is just figuring out how can we throw mass overboard more efficiently and at faster velocities. Now, we already know of one way to accelerate flow to very high velocities, and that's by using high pressure systems. And we can test this in the lab or at home by using a balloon. When we blow up the balloon, we compress the air inside and can see it pushing against the walls of the balloon. Now, if you give it an escape route or a nozzle, the air is going to rush out because gases will travel from areas of high pressure to areas of low pressure. And the momentum of the exhaust gases imparts a velocity on the balloon, giving us thrust. That is how cold gas thrusters work. And you can see them in action anytime you see an astronaut performing a spacewalk and using the maneuvering unit on their spacesuit to move around in space. But there is a limit to how much thrust cold gas systems can achieve. And that's because you need to use pressurized containers in order to contain that pressure. So what if we could create our own pressure? Specifically by looking at the relationship between pressure and temperature described by the ideal gas law. This law states that if we increase the temperature and keep the volume constant, we will also increase the pressure. There are two main methods of increasing propellant temperature. The first is by directly heating it. An example of this would be nuclear thermal propulsion, where you use the radioactive decay of uranium in order to heat the propellant, typically hydrogen. The second way of increasing our propellant temperature is by chemical reactions, which is also known as chemical propulsion. Now, there are many different types of chemical propulsion systems, but they all operate on the same concept. They use a chemical reaction between a fuel and an oxidizer to generate excessive amounts of heat, and therefore high pressure. The combustion process itself is quite simple, and it requires two very important components. The first is a type of oxidizer, which is typically some form of oxygen. Now, this oxygen can be a pure form like O2, it can be hydrogen peroxide, or any type of oxygen molecule. The reason we need oxygen is because oxygen is very effective, very good at breaking chemical bonds of compounds, which release a lot of heat. The next component is our fuel, which is any compound that has a lot of high energy bonds. And this can be a type of kerosene, jet fuel, methane, or even pure hydrogen. And when combined with oxygen, and sometimes a little bit of heat, they will react and release a lot of heat, called an exothermic reaction. We can even see it in action in a campfire. In this case, the wood is our fuel, and the oxygen in the atmosphere is our oxidizer. If we gently blow on the campfire, we are giving it more oxygen, which makes the flames hotter. This is exactly how chemical propulsion works, just with different types of fuels. Some propulsion systems, like the space shuttle main engines, use liquid oxygen and liquid hydrogen, because when combined, they release a lot of energy to bond and form steam. Other systems, like our Saltire 1 rocket here, use solid propellants, which could be either gunpowder or ammonium perchlorate, which generate very high amounts of thrust. There are also hybrid propulsion systems, like GU Rocketry's Chimera engine, which use both a solid propellant and a liquid propellant. And last, there's something we like to call monopropellants, because the fluid molecule contains both a fuel and oxidizer. Now that we figured out a way to get high pressure, there's another way to further increase our exhaust velocity, and that's by using a nozzle. By constraining the flow, we can actually increase the velocity at the throat and then later on in the diverging section. You can try this at home by putting your thumb over a garden hose. As you constrain the area, the flow accelerates and moves faster. Same principles apply to rocket nozzles to a point. Eventually, you can't make the nozzle throat any smaller because at that point the flow is supersonic. So what we'll do is use a converging diverging nozzle, a special type of nozzle which is able to further accelerate supersonic flow to even higher velocities and Mach numbers. And we'll explain how that works in a later episode on supersonic flow. Lastly, there's one other common method that we can use in order to increase the velocity at which we can throw our propellant overboard. And that's through the use of electric propulsion. Now, electromagnetic propulsion is a little bit different than traditional high-pressure propulsion systems. And instead of using a high-pressure system, it uses magnetic fields in order to accelerate single atoms or ions up to extremely high velocities. However, the drawbacks are that electric propulsion requires a large amount of electrical energy in order to operate, and it only generates a little bit of thrust, so it's not quite suited for using a rocket in order to get it off the ground. However, it is a very efficient way of generating thrust and is perfect for a lot of in-space propulsion applications. In any case, chemical propulsion is the most popular form of propulsion system, and each of its subtypes have different benefits and drawbacks to how they operate. However, they all operate on the same two principles. How can we throw more mass overboard, and how can we throw that mass overboard faster in order to generate thrust and high efficiency? And we use three main parameters to describe how good a rocket is at throwing that propellant mass overboard. First is thrust, impulse, and specific impulse. Thrust we've already talked about in the past, and it's a relationship of what the max force that the rocket engine can exert. Impulse is a description of the maximum change in momentum that the rocket can exert over the course of its burn time. And specific impulse is the change in momentum per unit of propellant mass that the rocket can produce. In other words, it's kind of a measure of efficiency. Solid propulsion, for instance, like the space shuttle solid rocket boosters, have very high thrust but low ISP, and they burn out very quickly, since solid rocket boosters throw a lot of propellant overboard very quickly. Liquid bipropellants, on the other hand, like the space shuttle main engines, have a little bit lower thrust than solids, but have a much higher ISP and efficiency, and a much longer burn time as they burn during the course of the flight. And depending on the application, different propulsion systems could be better than others. There is no overall best. Thank you to RS Grassroots for sponsoring this episode of the Sutton program. Head on over to designspark.com to read the article of this week's episode on propulsion. Thank you all for watching, and we'll see you next time.